Good morning, everybody. Today we're going to start chapter 2. Actually, we started it kind of last week. We deal with basic types, increasing, decreasing functions. Now we'll go into depth that, as well as talk about more the definitions of maximum minimas, relative and absolute, and then we'll finish up talking about piecewise defined functions. This is the one of the ones type of functions that give people the most troubles because it's multiple equations into one. So let's begin. Let's first look at increasing functions. And then we'll look at decreasing functions, and then functions that are neither increasing nor decreasing. Let's look at a graph. What do we know so far about this from chapter 1, about this graph? Yeah, we know the slope is positive. When the slope is positive, that means you have an increasing function. What that means, okay, here's our function f of x. At x1, there's a point on that graph that corresponds to y1. There's another point on this graph at x2. This point corresponds to another point on the y-axis called y2. The first point is x1, y1, and the second point is x2, y2. We always look at the x values. You notice the x is always going to infinity. So one of the conditions that we have to have is that x1 has to be less than x2. The x value of our first point is going to be less than the x value of the second point. Then, if y1 is lower than y2, the function is increasing. Let's look at an example here. We have 2 points, 3, 7, and -2, -10. If you're given 2 points and asking, is the function increasing or decreasing? One way you could do it find the slope, which we've done already for a couple of weeks. If the slope is positive, then we know it's increasing. That's one way of doing it. If I give you a graph, just look where the graph is going up to the right. That's an increasing function. Another method is rearrange them. Here's our 2 points. Remember what I said earlier, that x1 has to be less than x2. Is x1 less than x2? No. So let's rewrite them. X1 is now less than X2. All you do now is compare the Y values. Is Y1 less than Y2? Yeah. So because of that, we know that these 2 points are on a line that's increasing. The second method requires no math skills. Just rearrange them and compare. So let's look at decreasing is just the opposite. Decreasing, if you look at the graph, it's going down as you go to the right. Again, we have our 2 points. This is X1. It corresponds to a Y1. And this is X2. It corresponds to a Y2. The condition always has to be the same, as long as X1 is less than X2. If Y1 is larger than Y2, the function is decreasing. And of course, we see here that the function, the slope is negative. If you want to do the slope way, you get a negative slope. Here's an example. 3, 7, -2, 10. Positive 10 this time. Again, if you want to do the slope way, y2 minus y1, x2 minus x1, and the slope now is going to be negative. Rearrange them so that x1 is less than x2. So -2 is less than 3. So that tells us it's in right order. And we compare the y values. Is 10 greater than or less than 7? It's greater than. So y1 is greater than y2, which tells us it's going down. This is decreasing. If it's not increasing or decreasing, what else could it be? What would that mean, though? Horizontal, yes. What's the slope of a horizontal line? 0. Very good. So no matter what 2 points you pick on the graph, y1 equals y2. And if y1 equals y2, function is horizontal. Actually, there is one more, but we'll look at that one in a second. Three, 7, -2, 7. If you plug it into the slope equation, since y2 and y1 are equal, you'll get a slope equal to 0, which tells us it's horizontal. All the y values are the same. If you rearrange them, so -2 is less than 3, but we have 7 is equal to 7. So it's horizontal. Is there another possibility for neither? It's a vertical one. Very good. But the reason I didn't include it here so far is because a vertical line is not a function. Why is a vertical line not a function? Nope. The slope equals 0 is this one. It is a function. Well, let's look at it. We can look at a vertical line. Y1, y2. And they both equal the same x. So x1 equals x2. 2, 7, 2, 10. If the x's are equal, the line is vertical. Work out the slope equation of this one. Work out the slope equation. What's y2? This is x1, y1, x2, y2. So y2 is 10, y1 is 7, x2 is 2, 10 minus 7 is 3, 2 minus 2 is 0. If you have 0 on the bottom, what does that mean? It's undefined. If the slope is undefined, then you have a vertical line. That means your x's are equal. And by definition, it fails the vertical line test. The vertical line test says that any vertical line through the graph cannot cross the graph more than once. So when we talk about increasing, decreasing, when describing increasing or decreasing functions, we only discuss the domain. Of the function. That is the x values. And we only use parentheses. So here's our first example. All right. Here's our first example. Find the intervals on which the function of the figure below is increasing, decreasing, or constant. So it's increasing, decreasing, and constant. So where is it? Let's look at the graph. Where does it start off at? Where? Nope. Yep, because the line goes on forever. There's an arrow up here. So the line keeps on going forever and ever, slowly that direction. So it starts off at negative infinity. What's it doing from negative infinity to our first point? It's decreasing. So our first decreasing, parenthesis, negative infinity. From negative infinity, it goes to -1. That's where it's decreasing. What's it doing from -1 to 3? It's constant. So from -1 to 3, it's constant. And then from 3 to 5, it's increasing. And then what does it do after 5? What direction is it going? Down. So it's decreasing. So we have to put a union from 5 to positive infinity. Again, we never use brackets because you cannot use endpoints. We don't know what's happening at these dots there. For example, what's the slope at 5,2? What's the slope of the line at 5,2? The slope? Nope. Nope. Well, it is the function x squared, but actually negative x squared is opening down. But that's the function. But at 5,2, okay, what's the slope to the left of it? What is it doing? Is it positive or negative? It's increasing, isn't it? It's going up, so it's positive. So the slope here is positive, greater than 0. Over here, it's what? It's going down, so it's negative. So between positive and negative, what number do we have? On the number line, between positive and negative. Look at the number line. -3, -2, -1. 1, 2, 3. What's between there? 0. The slope here is 0. So it's neither increasing nor decreasing at that point. That's why we always use parentheses, never brackets. Yeah, I'm gonna spill the beans out here also. So look at 5-2. We call 5-2 an extrema. An extrema it's a highest or lowest point. If it's the highest, it's called a maxima. If it's the lowest, it's called a minima. The maximum, the minimum, highest and lowest. We have two types of extrema. So would this one be a maxima or a minima? It'd be a maxima. But is it the maximum over the entire graph? No, because these numbers here are all higher than this one. So there are two types. Of extrema. There is relative extrema. That means only in a small subdomain because the domain of our graph is what? The domain of our graph is from where to where? Yeah, negative infinity to positive infinity. That's the domain. But this one's the highest in some small domain, like from 3 to 7. So that's what you call a subdomain, a smaller domain inside the larger domain. So a relative extrema is only within a subdomain. We have the relative maxima and the relative minima. That's the first type. The second type is absolute. It's an absolute extrema. That means over the entire domain. So the absolute one are the highest and the lowest over everybody else. Can you have more than one absolute? No, there's only one and only one. Can you have more than one relative? Yeah. You can have infinite number of relative minimas and maxima, but there's only one absolute maximum minima. So these are the highest and lowest overall. So far, so good. Relative maximum minima, these extrema points. They have names. They're called vertices. This is plural of the word vertex. This is singular. So the vertex, you know, you have a vertex when your slope is equal to 0. Because it's neither increasing nor decreasing anymore. For example, the slowest part of a roller coaster ride is where? The slowest part of a roller coaster ride is at the very top of the climb. Where's the fastest part of a roller coaster ride? At the very bottom of a drop. When you start going up. The minute you start going up, you start losing speed. So the vertex, the vertices are your highest and lowest points of the roller coaster ride. All right, let's do another example. Using the graph below, determine any relative maximum minima of the function. F of x equals 0.1 x cubed. No, I want to talk about that. So, and the intervals in which the function is increasing, decreasing. So go ahead and work that out. One thing within the next few chapters, I need you guys to memorize the library of functions. Because you're going to get to a point where I can give you the function and you're going to tell me the graph. But just by looking at the equation, you can tell me automatically what the graph's going to look like. The largest exponent, this is called the degree. Since it's a cubic equation, we know cubic equations from the library of functions look like this. We know the shape of it now. We know something else without doing any math. What does this number represent? The y-intercept. The constant of a function is always the y-intercept. We know that the graph is going to cross at the number 2 on the y-axis. And since it's positive, we know it's going up like this. If it was negative, the graph would look like this. If it was a negative in front of the first number. That's the stuff. Again, I need you guys to memorize those library of functions. So you have a basic idea. Well, actually, we're going to do that in the end of this chapter. In section 5 or section 6, whatever the last one is we're going to go through all these transformations. So the faster you know those, the better you know those functions, the easier it's going to be for you. So The first thing we have the relative extrema. We have the relative maximum and the relative minimum. Where is the relative maximum at? Yeah, what's the point? What's the location? Negative 0.082, comma. Right. That is our relative maxima. What's our relative minima? Comma. Very good. Very good. Now, since we have relative maxima minima, that means, and they're not the same points, that means we have to have places where we have increasing or decreasing functions. Where is it increasing and where is it decreasing? So where is it increasing? Very good. It's increasing. This line goes on forever and ever, so it goes to negative infinity. So it's going from negative infinity all the way up to this point here. What's the x value? Negative 0.082. What's it doing after that? Is it going up or down or staying the same? It's going down, so it's decreasing from negative 0.082 to where? Right, 0.4082, 4.082. Remember, you only record the domain, the x values. Then at 4.082, it starts doing what again? Going up. So it's increasing. So we put a union, and it goes up from 4.082 to infinity. That's what the graph looks like. Yeah. So what's another name for both of these put together? What are those called? Starts with a V. Very good. Vertices. We know they're vertices because they're top and bottom, and their slope is equal to 0. We can now describe what's happening in the graph. The way we know we have a maximum or a minima, let's look at the graph we have here. We have these two parts of the graph. This is the point negative 0.082, comma 2.004. And this is the point 4.082, comma negative 1.604. We'll call this one A, and we'll call this one B. Since A is at the very top of this little bump, we know it's a relative maxima. That's point A, because the slope is equal to 0. What's happening to the left of A? To the left of A, the side. The way you can tell if it's increasing, take your pen. X always gets bigger. So it always moves to the right. What's the graph doing as I'm going to the right? Is it going up or down? It's going up. So on the left-hand side, it's increasing. The slope is positive. After the point, my graph is going down. So it's decreasing. And the slope is negative. So we know this is a maximum because on the left it's increasing, it's going up. And on the right, it's going down. So it has to be the highest point there. Relative minimum at point B, again, the slope is 0. To the left of B is the line going up or down? It's going down. So it's decreasing, which means our slope is negative. And then afterwards, it's going back up. So it's increasing. Our slope is positive. This is how, like in engineering and physics and the sciences, where we look at when things increase or decrease, we see a printout of numbers. On that sheet of numbers, you'll have something like 8, 8, 7, 4, 2, 0, 0, -3, -5, -8. What does that tell us? It tells us that on this side, these are the slopes. On this side, it's increasing because they're positive. We have 0, so it's horizontal. And this side, they're negative, so it's going down. So we have a spike, a high point there. And it tells us because we have a positive slope, then a negative slope. Between there has to be a 0. Okay. Next, we're going to talk about word problems. Actually, they have a way to make it less scary. Application problems. Application is just another way of saying a word problem. And word problems are not that tricky because, I mean, if you think about it, everything we deal with is a word problem. If I say, solve this problem, x plus 7 equals 5. I gave you a bunch of words, you put them in the symbols, and then you solved it. The same way you do this. So with word problems or real world problems, these are ones that you can actually relate to, you can actually use. There are 4, some people say 5, but there's something like 4 parts. 4 parts to solve a word problem. Next to fractions, these are the parts that everybody hates the most. Actually, I think they hate this more than fractions. So the first part, read the question and identify the information given. In math, when you read things in math, you're reading for specific content, specific information, as opposed to in history and anything else. English, you read for general content. Who's the star? Who's the heroine? Who's the villain? Who's the victim? But in mathematics, we have to look at what do these words mean? They all have special meanings to them. We have words that define values. What values are given? Figure out what they are, what they mean. How do they relate to the problem? You know, you have something to solve. How do those numbers fit into this whole scheme of things? What is the problem asking for? These are all questions. Once you do that, draw a picture if possible. Diagram what the question's giving you, what information, what it's looking for, because this way you'll have a better idea. A picture's worth 1,000 words. It may tell you what you need to use. Determine what formula is required to solve the problem. It may be given to you in this in the words or the picture itself. When you draw it out, it'll tell you. Then find the relationship between the values given and the problem stated, then plug them into the formula and solve. And then there would be a fifth step. So, okay, check your answer, make sure it has the right units, and make sure the answer makes sense to what you're being asked. All right. Here's this problem. Two nurses, Kiara and Mateus, drive away from a hospital at right angles to each other. Kiara's speed is 35 miles per hour and Mateus is 40 miles per hour. Express the distance between the cars as a function of time, dt. D is the distance, t is the time, is the variable. And then find the domain of the function. So, first step, what's given? Yeah. That's the first thing. That's important because what does that mean? They both start off from the same place and they both start off at the same time. Because if they didn't start off at the same time, then we have to have a shift in that time when the first one took off and the second one took off. So this one tells us that they both took off at the same place and they took off at the same time. Kiara is at 35 miles per hour. Mateus at 40 miles per hour. So Kiara is going 35 miles per hour and Mateus is going 40 miles per hour. There's your picture. There's your equations. What's the question asking for? What's the question asking for? Yeah, the distance between the cars. The distance. So looking at the picture, do we have a distance formula in mind? Because the distance from this car to this car, that's what we're looking for. We're looking for this distance. And it's a right angle, which means 90 degrees. Do we know any formula that deals with triangles and 90 degrees? A squared plus B squared equals C squared. C is the distance between these 2 points, between point A and point B. That's what C finds. So since it's looking for the distance, that's the hypotenuse. The hypotenuse is the distance. So looking at this formula, we have the distance squared is Mateus squared plus Kiara squared, their speeds. There's another formula that it gives us. The distance between, what is the formula for distance of moving objects? Because it's a car, what's the distance of a moving car? We also know that distance equals rate times time. Rate times time. How fast are you going for how long? So that's what these are. So the distance equation, it has to do with time. Why time? Because we know the rate. The rates are here. These are the rates. The only thing we don't know is time. So that's our variable. So what's the distance of Mateus? What's his rate? 40. What's his time? T. So that's his information. And Kiara, what's her distance? Rate times time. 35 times T squared. We're solving for distance. We have distance squared. How do we get rid of the square? Square root, both sides. So the distance with respect to time is equal to 40t squared plus 35t squared. Since they both took off at the same time, this will tell us the distance. This is question A. Question B is asking, what's the domain of the function? Is there any way this number here inside here can be negative? If you take a number that's negative and you square it, what happens? It becomes positive. So ideally, everything you put positive numbers in there, you can put negative numbers in there, and you can put 0 in there. So the domain you'd think is from negative infinity to positive infinity. But that's not right. Why is that not right? You cannot have a negative time. So what do you have in time? What's the smallest you can have in time? You can start off with 0 time. That's what they did at the hospital. Time was 0. Then they took off and it started clicking. So that's your domain. All right. The next word problem. Area. A community college has 30 feet of dividers to set off a rectangular area for a student testing center. If a corner of the math lab is used for the testing center, the partition needs only 2 sides of the rectangle. So in this case, it'd be easier if we draw the picture. There's the math lab. And we're going to put the testing center in one corner. That's the testing center. So what do we have? What information do we have? We know we have 30 feet of dividers set off in a rectangle. but we need two sides. So what length, what formula we're going to use? Do we know what formula we're going to use already? Area, yeah, because it says area of office, the area of the office. So what's the formula for area? Or yeah, and yes, length times width or base times height, whatever. Yeah, h times k, whatever you want to do. So here we have our length, and here we have our width, and we're looking for the area inside there. So what's our formula? What do we put in there as our numbers? Nope. You have, whenever you start off with this thing, you start off with, we don't know these lengths. So since we don't know these lengths, only thing we know is the total length is 30 feet. So if this side here is, let's say, X feet long, how long will this side be? If this is X feet long, nope. Whereas if we took X feet from 30, what do we have left? 30 minus X, exactly. Because since we don't know the dimensions yet, we're trying to find a maximum amount for this. If this is 10, then this is 30 minus 10. This is going to be 20. If this is 28, 30 minus 28 is 2 feet. So that's what we have to do set up first. So our formula we're going to deal with is X times 30 minus X. These are our two sides. So express the floor area as a function of the partition length. And there you have it. You could multiply these out if you want. X times 30 is 30x. Positive times negative is negative. X times X is X squared. All right, so there's our formula for the area. That's A. What's the domain of the function? The domain is looking for this. What's the smallest this X value can be? How far away from the wall is the smallest it can be? Zero. It could be against the wall. If this one's zero, what's this one then? If X is zero, what is this side? 30 minus, what is X? If X is zero, it's going to be 30. So that's your domain. Your domain has to be between 0 and 30. That's how much border you have. You can either use none of it or you can use all of it. Now, determine the dimensions that maximizes the area of the floor. The way we would do that is we take the equation, this, since the smallest is zero, if we put X being zero inside this equation, we get zero. And if we put 30 inside there, 30 times 30 is the same thing as 30 squared, so it's also zero. It's a quadratic equation. Again, if you memorize the library of functions, a quadratic equation looks like this. It's a parabola, but it's negative, so it opens down. So we know our graph will look something like this, where this is the feet and this is the area. This are my X values. The vertex, the highest point of this graph, will give us the maximum area. So the highest point is going to be halfway between the beginning and the end, which is at 15. If we put, this is my X. If we put 15, 30 times 15 minus 15 squared, we will get 225. So the maximum area you can have with this configuration is if this wall is 15 feet away from the wall. If that one's 15, 30 minus 15 is also 15. So perfect square is the best idea. You're going to have 225 square feet. Because your lowest is 0, your maximum is 30. Since this is a parabola, it's symmetric. So halfway through it, it's going to be 15. It's good. It will take a lots of practice. I'm not gonna lie to you. And draw the picture, look at it. You have to know how to read for, I mean, here it said area. Look for any math words in there. They relate to a formula. All right. The third part of this section deals with what are called piecewise defined functions. Piecewise. This is when a function is divided into two or more sub-equations. For example, here's our function. Let's say this one is x minus 2, and this one is x squared. Here's my domain for each of these functions. And the x here has to be greater than or equal to 2. So piecewise defined function is when a function is divided into two or more sub-equations. Each one has their own domain. each one having its own domain. And remember, the domain are the X values you can use. And you graph these on the same picture, on the same chart. So let's look at this. Let's graph this one. We have this equation. We use this equation whenever X is less than 2. Whenever X is greater than or equal to 2, we use this equation. Notice the domain has to go from negative infinity to positive infinity. There has to be an overlapping. It stops at 2 and picks up at 2. So let's look at the first one. F of X equals X minus 2. What kind of equation is this going to be? What kind of graph? We spent all of chapter 1 talking about it. Yeah, this is linear. It's going to be a line. Slope equals 1. Since we know it's a slope of a line, as an equation of a line, all we need is 2 points. Always start off from the endpoint. Even though you can't use it, I'll show you what we do with it. So when X is 2, we plug it into the equation for this one. So we have 2 minus 2 is 0. So when X is 2, Y is 0. I put an open circle there because I cannot use that 2. But it tells me it tells me where this graph stops. Now it says less than 2. So let's pick another one. Let's pick 0. Plug that in there. So we have 0 minus 2 equals negative 2. So at 0, we have negative 2. So this part of the graph looks like this. This is part A. Part B, I use this equation, x squared, whenever x is equal to or greater than 2. X squared looks like what? It's a parabola. It's a curve. Now, since I can start with this number. 2 squared equals 4. So at 2, I get 1, 2, 3, 4. And this time, since I can use 2, I put a solid dot. Because I can use 2. And let's pick the next one, since x has to be bigger than 2, so I pick 3. 3 squared equals 9. So at 3, 6, 7, 8, 9. I get 9. The graph will look like this. So that's all this really talks about is we take multiple functions and put them on the same graph. Let's take a couple of examples here. All this one's asking for, it doesn't ask us to graph, it asks us to find the functions. So f at negative 5, f at negative 3, f at 0, f at 3, f at 4, and f at 10. So the first one, which one of these three equations do we use? Equation 1, equation 2, or equation 3? Why? Very good. Because our x is -5. The only one it satisfies is x is less than -2. So we use this one. So this one, we use x plus 1. So we have -5 plus 1 is equal to -4. How about the next one? Which one? The same one, yeah. Because -3 is less than -2. So I use the same equation. X plus 1. So this is my x value. -3 plus 1 is -2. When x is 0, which one do we use? The second one, because 0 is between -2 and 3. So I use this equation. It equals 5. F of 3. Which one do we use now? The second one, because this one says x is greater than or equal to -2 or less than equal to 3. Since x is 3, we use this one, and the function is 5. When x is 4, x is 4. X is bigger than 3, so we have to use this one. So it's x squared. So plug in my x. 4 squared is 16. And f of 10, since 10, x is bigger than 3, 10 is bigger than 3, I use this one again. So I plug in my value of x. That's how you do it. You look at the x value, see which domain it fits in, and then follow that, use that equation. Now, each of these things represent a point on a graph. This first one, the point is at -5, -4. That's a point on the graph. This is my x, that's my y. This next one's at -3, -2. 0, 5, 3, 5, 4, 16, and 10, 100. So be very careful, because on your homework, I can ask you something like this. What is it looking for? I'm looking for the x value. So what x value has a y value of 2? -2, I mean. The y value of -2 occurs when x is -3. So you have to be able to go both directions. I can give you the y value, tell me what x it came from. I can give you the x value, you tell me what y value it is. Let's graph this one pretty quick. we have two equations. So the first one is g of x is equal to 1/3 x plus 3 when x is less than 3. That's what this one tells me. Then g of x equals negative x when x is greater than or equal to 3. So let's look at the first one. It's a linear equation because x doesn't have an exponent or it's not a special operation on it. It's a linear equation. When x is less than 3. So I start off with 3. If I plug it in there for x, the 3's cancel, leaving me with 1. 1 plus 3 is 4. So at 3, 4, I have an open circle. Because I cannot use that 3. I have an open circle. X is less than 3. So I use something smaller, like 0. 1/3 times 0 plus 3, that equals 0. So at 0, we equal 3. 1, 2, 3. And since it's a linear equation, we know that this part of the graph looks like this. This first one are all x's less than 3. So it's going to the left. The other equation is negative x when x is greater than or equal to 3. So I start off at 3. I get negative 3. 1, 2, 3. Since I can use it, I put a solid dot there. There cannot be any openings anywhere. Everything has to be connected. X is greater than 3, so I use 4. Plug 4 in there, I get negative 4. Yeah, I know it's linear, so it looks like this. All right, so take a picture of this one and bring it back on Thursday, completed. Or write this one down. This will be your homework assignment. Write it down or take a picture of it.